Bismillahirrahmanirrahim. Today we'll talk about regular languages. A language that can be defined by a regular expression is called a regular language. We already discussed what is basically a regular expression. So one of the most important question is, are all languages regular? No. There are some languages that are regular and there are some languages that are not regular. How we can prove this, that a language is regular or not? We'll see this also in the next lecture. So let's see, just focus on the regular languages. But before, beginning to prove, we discuss some of the properties of a class of all the languages that are regular. We already discussed some of them in the Kleene theorem. So we already saw in the Kleene theorem that if there is a language L1 and L2, if those languages are regular, so it means that when we need to take the union as well as the concatenation, and for example, if you want to take the star closure, they will also be irregular. So three properties we have already covered in the Kleene theorem. One is the union, another one is concatenation, and the next one is the star closure. So here the same thing, if we write L1, if L1 is one language, L2 is another language, if we are taking the plus or union, so it means that the resultant language, it consists of the language of all the words that are either in L1 or in L2. When we are taking L1 dot L2, it means it is concatenation. This is basically the union, and this one is the concatenation. It means the language of all the words that are formed by concatenating a word. So it is basically the dot, indicate the dot from L1 with a word from L2. And this is basically concatenation. This one is the union. However, the L steric means the string that are the concatenation of arbitrary many factors, which is the star closure. So the set of the regular language is basically closed under the union, under the concatenation, and under the star closure operator or clean star operator. So if L1 and L2 are the regular language, they are defined by a regular expression which is R1 and R2. So what we did then, R1 plus R2, when you have to take a union of two language, so it means you are taking a union of two regular expression. L1 dot L2 concatenation, so it means R1 dot R2. L1 star closure means R1 star closure. Therefore, all three of these set of words are defined by a regular expression, and so they are basically the regular language. So the proof of the theorem above uses the fact that what is basically the theorem was related with the regular languages. L1 and L2 must be defined by a regular expression. If they are, we know that if something is defined by a regular expression, can be defined by a regular expression if they are a regular languages. Regular language, you can also be defined in terms of finite automata or finite state diagram or machine, we can call it, as it so happens that the machine can also be used in order to prove the theorem, because even the finite automata, even the regular expression or the descriptive form, all are basically representing the same language. We already discussed about the union. So there is a finite automata which is finite automata 1, another finite automata which is 2, and there is another finite automata which is 3. Finite automata 3 is basically the union of finite automata 1 as well as the finite automata 2. This is another thing which is the concatenation, which is represented by dot. So we have finite automata 1 represented by regular expression 1, finite automata 2 defined by regular expression R2. There is a finite automata 3 which is the combination of R1 dot R2, which means the concatenation. The concatenation of two languages which are represented using this are also regular. Same is the case with the union. For example, you have L1 and L2. It means that it is actually all the strings in L1 followed by L2. Yani 0, 1, for example, L1 is one language containing 0, 1. L2 is another language containing these two strings. So when you take the concatenation, it is what we did. We'll take this 0, okay, and combine with these two. L1 combining with these two. The other one is basically the complement. If L is a language over the alphabet Y, then L complement, okay, be the language of all the strings of from this input that are not the words in L, because it is the opposite. Yani, if L1 is here, we have 0, 1, 00, and 10. These are four strings. So L complement will consist of all the words except yani these four words. For example, if L is a language over the alphabet A and B of all the words having double A in them, so L complement will be all the words that does not contain this double A. It is important to specify that the alphabet this or else the complement of L might contain, for example, it might, because here it does not, it's not allowed to have double A in the complement, so maybe it can contain any of the words that can be either, if the input consists of these things. So it might be cat, dog, or the frog. So these are definitely not in the string L. But make sure that the input should also contain C, D, G, and so on and on. Notice that the complement of a language L1 is the L1 is the complement of, this is a symbol of complement, so this is the complement of the language L1. And we know, as per the De Morgan law, when you take a complement and then again the complement, it will be basically the same language. So this is a theorem from the set theory. This is De Morgan theorem, but it can also be applied to the languages. If L is a language, then L prime, for example, if L is a regular language, L prime will also be a regular language. It means set of, of a regular language, they are also closed under the complement, same like the union, the concatenation, star closure, as well as the complement. So here we can see how we can take the complement. You can, let's discuss. If L is a regular language, we know that from the Klein theorem that there is some for sure, because if something is a regular language, there should be some finite automata for that language. Okay, and some of the finite automata, if it is a regular finite automata, so it will be a, there will be a final state, and maybe some or yani, some or maybe no non-final state. If we want to take the complement, what we need to do is there are some steps. First of all, reverse the final status of each state. It means that when all the states that are final, you have to make it as non-final, and all the states that were non-final, you have to make it as final. So we will see in the example, inshallah. If an input string formally ended up in a non-final state, so it will now end in a final state, and vice versa. This new machine will, what we have built, it accepts all the input strings that were previously, that is not accepted by the finite automata. So if whatever was accepted by L prime is not accepted, sorry, whatever is accepted by L is not accepted by L prime. So all the words in L prime, and reject all the input strings that the finite automata previously used to accept. So we can say that even therefore this machine accept exactly the language L prime. So by the Klein theorem, L prime is also regular. Let's see. Consider this particular diagram. This is my finite automata consisting of x1, x2, and x3. X1 is the initial state, x3 is the final state. As per the algorithm, what we need to do is how we can take the complement. You have to convert all the non-final states into final. So this was non-final. What we did, we make it as final. This was also non-final. We make it as final. And the one that was final, we just make it as a non-final state. So this is basically a complement. For example, if we have this particular diagram, if you can see this diagram, in this diagram, this is my initial state. Okay, this is my final state. These are two intermediate state. However, this one is like a trap. So this language accept what? This language accept, you can see A, B, and here A comma B. So it can either accept A, B, A, or it can either accept A, B, B. Okay. Now, if I need to take the complement, okay, so it means it will accept all the words except yani these two. But as per the algorithm, how we can do it, whatever is the final state, make it as non-final. So this will be the non-final state. This will be my final states. Okay, and this one is also, what we did, we will make it as final. So here we can make this one as, this is my initial, and this will be final as well. This will be final, final, and final. However, this will not be the final state. Okay, so notice that we have to reverse the final and non-final status of the start state as well. Now let's do the last one, which is basically the intersection. If L1 and L2 are the regular language, so L1 intersection L2 will also be a regular language. It means it is basically the set of the regular language is also closed under the intersection. It is closed under the complement, under the union, under the concatenation and star closure. So here it is also common under the intersection. You know about this one, okay? So we can do the intersection by using the De Morgan law. Why? Because we already know how to take complement. We already know how to take the plus union. So it is easier take the complement and then take the union. So if L1 and L2 are the regular language, then L1 intersection L2 is also a regular language. So you can do it by using the De Morgan's law. You already know about the De Morgan's law. Okay. Let's do it by using the finite automata. You know that finite automata 1, finite automata 2, the intersection is basically, the intersection is equal to basically what it is equal to the complement of finite automata 1 union complement of finite automata 2. So what we need to do is, first of all, in order to apply the intersection, we already know how to take the union, we already know how to take the complement. So we will here, first of all, in order to apply the intersection, we'll first take the complement of both the finite automata, then we will find out the union, and after that we need to take the complement again. Why the complement again? Because I just need to take the intersection without this complement. So let's assume, let's do one of the example. For example, if L1 is the language that consists of double A, we have L2 that consists of even number of A's. Okay, if I need, for example, these language are not the same. Why? Because, since 3 times A is in L, 1, but it is not in L2 because 3 is not a union, number. So same is the case, ABA, okay, is in L2 because in case of ABA, what we have, it is even number of A's, but it is not in L1 because it says double A, yani 2 A's should be together. They are both the regular language because they can be defined by a regular expression. So here you can see this is the regular expression for double A, and this is the regular expression of having even number of A's. So this regular expression is represented by this finite automata. This regular expression is represented by this finite automata. Now let's take the intersection. First of all, we need to take the complement of F1, FA1, and we need to take the complement of FA2. How to take the complement? We need to make all the initial, non-final states to final state, and previously whatever was the final state, we will make it as the non-final. So here what we did, we take the finite automata 1, we take the finite automata 2, and we take individual complements. After that, we take the union. We already know how to take the union. We actually did it in the clean theorem. Then after taking the union, we came up with the, for example, this, let's assume whatever we will do, we will take a union, okay, after the whatever diagram we will get, and at the end, what we need to do is, again, we need to take the complement. In the complement, we need to make all non-final states to final state. So this is the final answer. You can try it because you already know how to take the union, you already know how to take the complement, you already know how to take the, and we already discussed how to take. Then after about the regular language, as per the regular language we came up with the conclusion that if a language is represented by a regular expression, it can be represented by a finite automata. The other thing is regular languages are closed under they are closed under the union, under the intersection, under the complement, under the concatenation, and also under the star closure. Thank you very much.